Series of diagonalizable matrices continue. If A is a diagonalizable matrix, then A raised to n is always a diagonalizable matrix. But the converse does not hold true always. That is, if we have a matrix whose nth power is diagonalizable, it does not guarantee that the matrix A is diagonalizable. Let's look at an example. Consider matrix A equals 0, 1, 0, 0, and we have the square of the matrix A square equals the null matrix. Let's check the diagonalizability of matrix A square and A. Consider matrix A square, which is the null matrix. Null matrix can also be considered as an upper triangular matrix or a lower triangular matrix. And the eigenvalues of upper triangular matrix or lower triangular matrix is just the diagonal entries. So here we have A square has eigenvalues 0, 0. We may also verify it using the characteristic equation, determinant of A square minus lambda I equals 0. We have the equation lambda square equals 0, which gives us repeated roots for lambda, which is 0, 0. Corresponding to lambda equals 0, assume that x1 is the eigenvector. We wish to find out the expression of x1. We have the matrix multiplication A square minus lambda I into x1 equals 0. After multiplication, we obtain the equation 0x1 plus 0x2 equals 0. Here, x1 and x2 are both free variables because whichever value you give for x1 and x2, this equation is preserved. That is, LHS equal to RHS condition is preserved, whichever value you give for x1 and x2, whether it is 0 or non-zero. Since we have to maintain the non-zero condition for the eigenvector x1, we assume that at least one of x1 and x2 are non-zero. That is, you write an eigenvector x1 considering x1 equals 0 and x2 equals non-zero. We have x1 equals 0 k. Next time we assume x1 equals non-zero and x2 equals 0. Then we have the eigenvector x2 equals k0. At least two linearly independent vectors we could find corresponding to the eigenvalue lambda equals 0. Since the order of the matrix A square is 2 and we obtained two linearly independent vectors, we can conclude that A square is diagonalizable. We may also find out other linearly independent vectors corresponding to lambda equals 0. But the existence of two linearly independent vectors guarantees that this matrix A square of order 2 is diagonalizable. Now let us check whether matrix A is diagonalizable. We have A is also an upper triangular matrix, hence the eigenvalues are the diagonal entries, which are lambda equals 0, lambda equals 0 here. We may also verify it using the characteristic equation determinant of A minus lambda I equals 0. We have the equation lambda square equals 0. So here also we obtain repeated roots lambda equals 0, 0. We wish to evaluate the expression of x1, which is the eigenvector corresponding to eigenvalue lambda equals 0. We consider the matrix multiplication, matrix A minus lambda I into x1 equals 0. And using the matrix multiplication, we have 0 x1 plus x2 equals 0 with the first row multiplied to the column matrix. We see that x1 is the free variable here and x2 equals 0. x1 is a free variable because whichever value you give for x1, LHS equal to RHS is satisfied for this equation. Since we have to maintain the non-zero condition for the eigenvector x1, we shall have to assume that x1, which is the free variable, should always be a non-zero value. So we have the general expression for the eigenvector x1 as k0, where k is not equal to 0. Since only one linearly independent eigenvector was obtained here and the order of the matrix A is 2, we will conclude that matrix A is not diagonalizable. The key observation that we made here is that even if A square was a diagonalizable matrix, A is not diagonalizable. So A raised to n is diagonalizable does not always guarantee that matrix A is diagonalizable.